I am on. And we'll just wait for sure.
Okay. So for our last session of the day, we're very happy to have Tom LeCompte here telling us about what have we learned from the LHC.
So I'd like to thank the organizers for inviting me and thank them again for being flexible because I had a meeting in Washington yesterday. One of the things you might be surprised, I'm now a mindless bureaucrat. When you've ever wondered who makes these kinds of bonehead decisions, that would be me. So I'm kind of hoping this will be more of a dialogue than me yammering on, partly because I suspect this audience is not the sort that would like to see the usual death march through plot after plot after plot after plot. So I took a little liberty in the title, and rather than I like the word learned as opposed to something like measured. I could tell you what we've measured and give you measurement after measurement after measurement, but I'm going to try and put it into some sort of context. And you can agree, and in some cases, you can disagree with the way I've kind of shaped things up. So by all means, yell, scream. I talk too fast. I know I talk too fast, and after 20-some-odd years doing this, I'm not going to change. So if you don't want me to talk too fast, you have to slow me down by asking questions. All right. So who is this guy? So. There's a picture of me there. I started my career in fixed target, but quickly moved into hadron collider physics. I've worked at CDF at the Tevatron, StartRIC, and Atlas at the LHC. I was the physics coordinator of Atlas when we turned on, and I've worked kind of in many different places. I have two kind of shticks. One is I find something that the experiment was not really designed to measure and measure that, rather than to climb my way to the top of the thing everyone's trying to do. And the other one is to kind of sit on the boundary between precision measurements and searches, because if you're looking for an excess, you have to know how many you expected. So I kind of sit there. All right, I'm going to start with conclusions for a couple of reasons. One is those of you who want to play soccer will have an opportunity to leave, and they will have seen the important parts. If we get stuck on some technical point, you will have at least at some point heard what I'm going to try and say. And like I said, the soccer's calling. So what have we learned? We've learned there are exactly 3 generations. We've learned that nature has provided a fundamental scalar, and as far as we can tell, its properties match the standard model Higgs, and its mass makes absolutely no sense whatsoever. And the Higgs mass is suggesting that there's new physics at the TeV scale, but Flavor is suggesting that it's more like 10 TeV. So this is the tension that this generation of scientists is going to have to try and sort out. All right, so let's start with the argument for 3 generations. I should apologize. I really prefer Blackboard talks for this sort of thing. But since I was asked to provide the slides ahead of time, preparing the notes was just as much work as preparing the slides. So everything's going to be on slides. And I'm working only one side of the room. So this is the Feynman diagram for 90% of Higgs production. It's called gluon fusion. But what really happens is you've got the gluons come in. There's a virtual top loop that's sitting in there, and the Higgs is radiated off. All right, so you would think if there's some other new particle here, well, it's going to be suppressed by the mass because it's running in a loop. And that's true, but the Higgs coupling is proportional to mass. And it turns out those exactly cancel. So the amount of Higgs production you get is independent of the mass that's running around here once you get above about the top mass. All right? So that's the idea. If there's a 4th generation, I need a T and a T prime. Right? T prime and a B prime, because I don't want anomalies in the theory. Right? And if I want the true 4th generation, I have to copy the whole thing. So instead of one guy running around in the loop, I've got 3 guys running around in the loop. So the cross-section of this process goes up by a factor of 9. And we can usually tell a factor of 9. If you don't believe me, I drew a factor of 9 in on this plot. So what we've said with 3 generations is the red curve, and with 4 generations is the blue curve. This is not this tiny, subtle effect. This is huge, right? I'm sorry, my new boss. This is huge. Now, there's a couple of silly ways you can look at this. One of them is you can say the number of generations is 3.00 plus or minus about 0.04. I think that's a particularly silly way. The other is we're actually more confident that there are 3 generations than there are 4 and not 4 than we are that the Higgs exists, right? Because the red line is farther from the blue line than it is from the dashed line. So we are really, really sure. You've got a question coming up.
This factor of 9 depends on the fact that the fourth generation couples to the gluons in the same way as the...
Okay, this means I'm going through the right material, but not fast enough. Let's talk loopholes. All right? So, loopholes. What are we assuming? This assumption is this fourth generation is absolutely sequential. I take the third generation and I make a fourth generation that looks exactly like it. So what's required? As you say, the couplings to the gluon have to be the same. It has to be chiral. Because to get the Higgs-Yukawa, what does that mean? It means I take a left-handed field, I take a right-handed field, and the Higgs-Yukawa couples those guys together. Right? So the whole argument about the mass means this fourth generation has to get its mass from the Higgs. So what are the ways around this? One is the families could be vector-like, not truly sequential. So there could be a T prime, there could be a B prime, but they don't fit in like the standard model. They're their own kind of things. They get their mass through a mechanism other than the Higgs. Completely possible. Another one is that maybe there's lots of Higgses out there, right? And the 3 generations that we know they get their mass from Higgs number 1. There is a 4th, 5th, 6th, 10th generation out there that get their masses from Higgs 3, 4, and 5. There's no problem with that from the measurement that I've made. And because I'm like being pedantic, strictly feel it's not a Higgs boson they get their mass from. They get it from a Higgs field, which gives them a Higgs boson. And then there's always the miraculous cancellation in theory. 2 new things happen. One of them does the thing that you're interested in, and the other one covers up its fingerprints from all other indirect measurements. So you can always have one of those guys there. But I think it's still, even ignoring these loopholes, this is really, I think, the most surprising fact that came out of the LHC. There are 3 and only 3 sequential standard model families of fermions. And if there's a 4th, it's either vector-like or it's a child of another Higgs. There's something different about it. Now, I've been talking about, oh, yes. A vector-like family, so a chiral family is one where the left and right-handed spin fields hold different quantum numbers. A vector-like one is one where they have the same quantum numbers. So vector-like makes sense. Chiral makes no sense. Nature has decided that it wants to give us chiral guys and not vector guys. I was not present for that decision. If I were present, the universe would be a lot better ordered than it is. All right, so how do you know this thing is the Higgs anyway? This is a plot of LHC data. This fellow over there is the Higgs boson. You can see that peak there. What am I plotting? I'm plotting the invariant mass of an on-shell Z and an off-shell Z in 4 leptons. So I take the 4 lepton invariant mass. There's an edge here where I start to be able to produce 2 real Zs. This thing is a background from 1 Z decaying to 4 leptons, and then there's the Higgs. So this particle is coupling very, very strongly to an on-shell and an off-shell Z. It's about 20 widths away from the pole, but it's still one of the dominant decays. So this thing wants to couple to the Z like crazy. It also wants to couple to W's. Same argument, lousy plot. All right, so if I made the equivalent picture, you wouldn't see this. So and this thing basically is coupling with strength 1, which is exactly what you expect in the standard model, because what is the Higgs and the Z? Well, the longitudinal component of the Z is left over from the Higgs field after it gets eaten. So it's the same particle in some sense, and that's why the coupling is 1. Now, even if we're completely wrong about the Higgs, the fact this couples this strongly means you can't write down a theory of electroweak symmetry breaking that doesn't include the particle discovered at the LHC and have it possibly be right. So even if we're wrong about whether this is the Higgs, it is playing a huge role in electroweak symmetry breaking. It also turns out the spin parity appears to be 0 plus, the production rate matches theory, and the mass is consistent with what precision electroweak tells you the Higgs should be. That's actually only logarithmic, so the fact that it's on the plot is pretty much all you can say about that. But as far as we can tell, this looks really, really Higgsy. So I mentioned that the couplings were what you expect. I think it was Scott Thomas at Rutgers who first took this plot. You put the mass on this axis and the coupling that it needs to be, whether it's a boson or a fermion, and you see all of the particles line up exactly where the standard model says. So you think, this is good news. And it is. But there's a little bit of a hitch to this. The experimental sensitivity is roughly where I drew the red line. So the fact that everything is sitting just above the red line is, yes, it's what nature is telling us, but it's kind of the only result that could possibly have come out of the experiments. Right? If you're below the red line, you wouldn't see anything at all, and we'd be asking the question, where is the Higgs? Right? And if you're substantially above the line, the Tevatron would have found it years earlier, and you wouldn't have me talking in front of you, you'd have somebody else. So there's kind of an anthropic argument that the fact that I'm giving you the talk is telling you that you're more or less in the standard model ballpark. Right? So it's good news-ish. You have questions, comments? No, of course not. All right, so let's talk about everything we know about the Higgs coupling to the first and second generations. And it's on that slide. We produce this through gluon fusion, which goes through a top loop, third generation. WW fusion, not having anything to do with the generations at all. We know absolutely nothing about this Higgs in the first and the second generation. Yes, we know the mass of the electron, but we have no idea that the electron couples to this Higgs and not some other fundamental scalar. I could write down a theory, even I could write down a theory, where you have two Higgses. Higgs A weighs 125, couples to the third generation and only the third generation, and the electroweak bosons. And some other Higgs deals with everything else that we see. And I challenge you to come up with an experiment that can separate those. But there is hope. So anyone want to guess what you would try and do to get the Higgs coupling to, say, charm? Or does anyone want to guess anything at all? I could just start calling questions. What's your favorite color? So what is not going to work, oh, I got this wrong, is that. So you'd like to look, the simplest thing to do is to say we're going to make the Higgs, and then we're going to look for its decay and find out if any of the decays is charm or strange, and does this. I mean, this sounds obvious. Why doesn't it work? Well, even this doesn't work. And the answer is the Higgs is produced with electroweak size production rates. Quarks are produced with QCD size production rates. So the number of BB bar events that I have is something like 10 to 50,000 times the number of Higgs events that I have. All right, so to get a statistically significant sample of Higgses in a peak, you've got to run for a zillion years. All right, so BB bar by itself is hopeless. We can see it only in cases where the Higgs is produced some other way, for example, in association with a W or a Z. CC bar, is the coupling going to be larger or smaller than BB bar for the Higgs? Smaller, right? Because the mass is a third of that. Right? On the other hand, the background is 2 or 3 times larger. So you're moving in the wrong direction as you go lighter and lighter and lighter. Right? Your backgrounds get bigger and bigger and bigger, and your signal gets smaller and smaller and smaller. Furthermore, the way we find C's is really, really icky for this. Right? The way you find a B is you look at a jet of particles, and you say, some of the tracks that are coming out of there don't come from where the particle started from. All right? That lived a long time, produced a B, and they don't come to the primary vertex. Now, when I replace the B with a charm, a couple of things happens. One, the average lifetime is smaller. So I move this point in. The C is lighter, so I produce fewer secondaries, so it's harder to spot this vertex. And because it weighs less, the explosion isn't as spectacular. So instead of this, you get something more like this. Now what's a light quark? Well, that's just everything comes from the same point. Right? Now you've got the Goldilocks problem, right? You're trying to find something in the middle of these two guys. And you're making errors on both sides, and you really, really have to know how well you're doing to make sure that you're not actually seeing this that masquerades as this, or this that masquerades as this. So experimentally, it's hard to find CC bar. If I go to SS bar, again, I'm moving in the wrong direction completely. So production is not what we want. Let's think about decays. Most of the time, you get two jets, and I just told you this thing is hopeless. But these guys can get closer and closer and closer to each other if I allow one of them to radiate a photon. So if I have Higgs goes to J psi, which is CC bar plus gamma, this rate is related to the CC bar coupling. Now, this is a really terrible way of doing the measurements because most of the time this doesn't happen. You're only looking at that 1 in a zillion chance where everything, stars line up just perfectly. Right? Why are we thinking along these lines? Because we don't have a better alternative. If I build an E plus E minus collider, I can increase my number of Higgses, but I can't make them decay the way I want to any better. So the question is, can I make a Higgs out of E plus E minus? And the answer is you can, but it's really, really hard because as you said earlier, the coupling to electrons is small. I want to measure a couple of things, right? I want to measure its coupling to the second generation, and the first would be even better. The problem is you're down by this huge mass factor. Right? And people are even talking about even crazy things like using muon colliders to do this, because as hard as it is to do a muon, it's 40,000 times easier than doing it with electrons. So this is one way to get at CC bar. SS bar, it's a phi. Mu mu, the experiments are talking if you just got enough Higgses, we think that you could see a mu mu bump. But we're talking 2025 and beyond before we collect enough data. So it's going to be a long slog before we really know what's going on with generations 1 and generations 2. Yes, with a muon collider, if you could build a muon collider at all, the tuning to the resonance part is easy. The hard part is getting the muons up to the right energy, before they decay. I've seen no reasonable proposal of getting enough electrons to do this. The problem you have is electrons repel each other. So when you try to get them into a small enough space to produce the Higgs in the rate that you want, they fight back. And when they fight back, they radiate photons and they lose energy. And now they move off your peak. No, but the bunches of electrons and positrons, they spend most of their time getting accelerated and only a little tiny bit of time as they collide. So you're right, yes. During that brief instant, life is good. But getting there, it's like the family trip to Disneyland. By the time you get there, everything is fine if you still have a family at the end of the trip. All right, so we talked about the Higgs. That was just me talking about the Higgs, right? What if it's 2 Higgses or 3? I mean, if nature permits a fundamental scalar at all, why stop at 1? Right? If it's going to do something crazy like create a particle with the quantum numbers of the vacuum, right? Why not a zillion? So to keep our sanity, we think about 2. And that's not necessarily dumb. because even if there are 10 out there, before we know there are 10, we're going to know there's 1, and before we know that there's 10, we're going to know there's 2, and so on and so forth. So the framework that people like working in is what's called the 2 Higgs doublet model. And there are 4 types. You can say fermions see one Higgs, bosons see another. Or you could say the up-type guys see one and the down-type guys see another. And then there are horrible combinations of things where you're coupling to the up guys of this guy and the down ones over there. If I have 2 Higgs doublets, I've added 8 degrees of freedom to the system total. 3 are needed for electroweak symmetry breaking. That leaves me with 5. And you have 2 neutral guys that are CP even, 1 that's CP odd, and 2 charged guys. SUSY forces you into what's called a type 2 model for reasons which I have had people explain to me in using words like holomorphic, which I understand means something. I'm an experimenter. It's like, okay, whatever, fine, great. Really, there's kind of 2 words or two parameters that describe this. One is this alpha guy, and that's a mixing parameter. It says when I write down when I go from writing down 2 fields, phi1 and phi2, how much of that is in this guy? And of course, the orthogonal combination is that guy. So that's just a plain old mixing angle. If I have 2 different Higgses, they have 2 different vacuum expectation values. So I can divide those, and I can call it a ratio, and that gets me beta, which is technically the arctangent of this ratio. And like I said, people explain why this is so by reasons that I don't know. I am an experiment. Have any of you seen experimenters before? Am I the first experimenter you've ever seen? just curious. So there's 2 possible ways of going after this. The first one is direct observation. We've kept up the Higgs search even after we found the Higgs, not because we don't know when to stop. Like, when you find your car keys, you usually stop looking for them. We haven't. We're continuing to look for the Higgs because if we see another one, that would be interesting. But also, you could look at the guy we found and ask, what are the possible, what are the deviations that this thing may or may not experience from the standard model? So if, for example, it did not couple to the W and Z as strongly as it does, you might say, I'm not getting enough electroweak symmetry breaking from this. Something else has to be causing it, and that would be a reason to look for another Higgs, or Technicolor, or this or that. One of the problems of going from notes to slides is there's stuff you need to know and doesn't fit anywhere else. So here's a page of random facts. Random fact 1. In SUSY, the mass of the lighter Higgs at tree level is the mass of the Z times cosine of 2 beta. And that implies, since cosine of an angle is less than 1, we hope, the Higgs is lighter than the Z. When I was going through grad school, the one thing we were absolutely sure of is the Higgs weighed less than 90. We're absolutely positive of that. Turns out to be wrong. So this is a tree level statement. So it could imply radiative corrections are large, or it could imply we found the wrong Higgs. That the light guy, there really is a light guy sitting underneath the Z mass, and the guy that we found is the heavy one. That's okay. Christopher Columbus discovered the wrong thing. Turned out okay for him for a while. So the direct searches, as I said, we're just repeating today's search. We have about 5 times as much data. Yes, he was killed by Indians. Oh, that wasn't your question?
So this statement is generic in SUSY model, so it's a message.
The statement that Columbus was killed by Indians? It is a generic statement in SUSY models, but you're going to see in about 2 slides that this statement is based on a bunch of assumptions that we know are not true. So I'm not sure what you say about this, right? It's a statement that's generic and wrong. Anyway, we'll get to that in a bit. So as an experimenter, unfortunately, we can only measure a few things. We can measure the topology, right? What did we have in the event? How many electrons, how many muons, how many of this, how many of that? We're pretty good at that. We can measure cross-sections, which is just a fancy word for rates. Do we make 10 of these guys, or 100 of these guys, or 1 million of these guys? And then there's kinematics, energies and angles and the like. Right? As you go down and down, it's less constraining to the physics. It also happens to be harder to measure. We are very fortunate that both arrows point in the same direction. If one went up and one went down, it would be very bad because you'd have good measurements that told you nothing and bad measurements which are exactly what you wanted to know. Okay, enough random facts. So let's say the Higgs we have coupled only to bosons. Oh, I'm still working on this slide too much. When I'm working to that side of the room too much, you tell me that. That's your job. So, suppose the Higgs coupled only to bosons. What would happen? Well, the branching fractions to quarks goes down because they're fermions. So the branching fraction, which is constrained to be equal to 1, when you sum them all up, that has to go up. So branching fractions to W, W, Z, Z, and gamma, gamma all go up by a factor of 10. This production rate, which has this fermion through here, which I said was 10%, goes away. You're left with that. So the cross-sections go down by a factor of 10. The branching fractions come up by a factor of 10. And you're right where you were. So at some level, you would say, God, we're not sensitive at all. This thing might not even couple to fermions. We might just be confused. It's not as easy as it looks, but it's not as hopeless either. So that rate, total rate, is actually less sensitive. I'm okay? Okay. Good, good. Good? But what does change are the number of associated jets. I have to go back here. I won't go all the way, I promise. So this shuts off, this turns on, and I have 2 more quarks in the final state. Yes?
Wouldn't this drastically change what we estimated the G-2 of the muon to be?
There are lots of indirect effects. I don't know if this particular one changes G-2, because I don't see a Higgs loop in that.
I mean, you get a Higgs contribution at sort of like 1 loop level, G-2, and then you have to worry about if that's gone.
So I am not an expert in that. So I don't know for sure. But I don't think the Higgs loops are the ones that are dominating. But, I'm just making this up because I can. So what do we really have? So we have the number of associated jets. And if you look at this, what we really have, in this case, are the rates, the kinematics, and what's produced in association from all of these particles. But we really have only 5 measurements. 2 photons, W, W, Z, Z, taus, and B's that are associated with W's and Z's. So when you see the experiments say, we've measured 18 different couplings, they have, but they're correlations that are built in, and we're not telling you about them. Generally what you do is you say, let's assume there's only 1 bit of new physics that changes only 1 parameter in the model and everything else stays exactly as it was. That's probably not what's going to happen, right? If there's going to be new physics, it's probably going to have its fingerprints in many, many different places. But we have to say something. So these are plots of the allowed... I'm going to go over here, just to spite you. These are plots of the allowed regions for the 4 different 2 Higgs doublet models. These plots are completely unintelligible. This direction is the mixing term. This direction is the difference in VEV term. And you see that none of these, have a lot of constraining power near the middle. That's because that's the case where one of the Higgses looks very, very standard model-like, and the other Higgs looks very, very different. Since the guy we found looks very, very standard model-like, you don't have much constraining power over how different the second guy looks, because you have no real information on the second guy. So that's why it looks like this. You get these lobes because of quantum mechanics. You have to add amplitudes. So there are reasons that you can get the same intensity coming from 2 different amplitude processes, so you can't distinguish between them. And then everything else that's yellow we don't see. So if you just kind of look at this plot and someone asked, how well do we know the couplings? You can say, well, look, 1% is too small and 50% is too big, so some number around 10 to 30%. And I think that's the sort of carry away I would like you to have, is that we know that this Higgs is good to, looks like the standard model, but at the 10, 20, maybe 30% level. If it could have a lot of deviation, and we wouldn't be able to see it if you think 30% is a lot. Right, so it looks like the standard model Higgs, but this is hardly a precision measurement. And this is why the experiments want to collect more and more data. Because the more data we have, the more of these points we can exclude. And if we find, for example, that the excluded point is moving away from the standard model point, which, by the way, is here, we would then be able to say, aha, there's something else going on, even if we don't see the other Higgs that's the orthogonal combination. If we can study this one well enough, that's something we will know. I'm not going to talk about the mass yet, because there's one thing which is just cool. Not as cool as the German word for spherical harmonics, but still cool. So, I don't want to erase anything either, but I'm going to. Well, I've got a spot here. So I said the Higgs was a 0 plus particle. How do I know that? And you will see papers by the collaborations where they say, we took every possible observable and we ran it through this complicated Monte Carlo, and this is what came out. And that's absolutely true. It also gives you no insight whatsoever about why. Right? The Higgs mass, I'm going to kill all your chalk. Say I've got Higgs going to ZZ star. Well, the mass, the Higgs, when it decays, the mass has to go somewhere. So it goes either into the first daughter, or it goes into the second daughter, or it goes into kinetic energy. Right? Halliday and Resnick argument. What's kinetic energy? It's L squared over 2I. This number is 90 GeV. All right, this number is 125 GeV. And that's something that you measure. So there's an anti-correlation between the mass of the second guy, which is off shell, and how much angular momentum is there. This is why, before we published anything, I looked at the mass plot and said, the Higgs is a scalar. Because we had events that are so far out there, you don't get them when it has other decays. So because we had very heavy guys with the Z star, the off-shell guy, that tells me that there are events where the angular momentum is very low. And that tells us that you've got a scalar. So the scalar, this distribution looks like this. If it's a pseudoscalar, it looks like this. And the bigger the angular momentum, the more to this side of the plot the curve goes. So you're not actually in an eigenstate of angular momentum. So I'm declaring the kinetic energy to be equal to the angular momentum squared over 2I. I'm defining the angular momentum in such a way to make it that way. It's a cheat, but if you think about what you're really doing, right, where else is it going to be? It's going to be in the kinetic energy of the two, right, of the system, which you can always pick a frame where that's 0. Right, and I've defined angular momentum about the center of mass of that point so that everything is allowed to go in there. So that's the easy to see argument that is captured in this complicated Monte Carlos with angles and dangles and all of this. But what's really going on is very simple. The other thing you'll see is people think that the angular decay of the Z matters, but it doesn't. And that's just a numerical accident. The Z decay to leptons goes entirely through an axial current. It's a gamma 5 gamma. And there's only like a 3% contribution of just a gamma 5, or just a gamma mu. So there's no parity violation in the decay to speak of, so it forgets anything it ever knew about its parent's angular momentum. So everything gets captured in the linear piece. It's just a gee whiz fact. You should know this because it's true, we never say it. There are people in the world who think that the way to move up in physics is to take something simple and make it complicated. I think it's better if you do the reverse. You take something that's complicated and make it simple. All right, so let's talk about the Higgs mass. that I've been saying 125, 125, 125. Does this make any sense? And the answer is it doesn't make a lick of sense. The Higgs is way too light to be heavy, and it's way too heavy to be light. So I did this right. I put the square in because I knew I was going to be talking to people who were mathematical experts. The physical mass of the Higgs squared is its bare mass plus the radiative corrections. All right, now radiative corrections are of order alpha weak. That's a weak process. Times whatever your new scale is over 4 pi. And there's potentially an enormous amount of new physics up there, right? There's the Gut scale, the Planck scale, all the cool stuff is happening up there. Why does the Higgs, which has the same quantum numbers of the vacuum, not see all of these things? So this will tend to drive the Higgs mass up and up and up. Michael Dine put some numbers in here just so you could sort of see. I mean, these numbers are made up, but they give you the right mass. And the idea is, well, maybe 35 digits down, everything is exactly the same. And the last few digits are slightly different, and that's why the Higgs mass is light. This looks absurd. Why does it look absurd? Because it is absurd. He made it up. But he made up numbers that had lambda at roughly the Gut scale and ended up with the observed Higgs mass. So he said the bare mass had to be some other thing. But it's all made up. Because the bare mass and the radiative corrections have nothing whatsoever to do with each other. Right? The bare mass just is. The radiative corrections somehow probe this entire scale. Right? And because these things don't have anything to do with each other, it's really hard to imagine how it works out that the Higgs mass ends up at the electroweak scale. So let's talk about fixing the problem. So we have 3 choices here. We want to know why are the bare mass and the radiative corrections about the same size. Idea number 1 is it's just an accident. Had to be something. This is what it is. Now, I don't mind accidental explanations for some things, like why do the sun and the moon have the same angular size? And the answer is, well, it's just an accident. It's also something which changes over time. You can ask the question, why do we live in a time where the sun and the moon have exactly the same angular size? The answer is it's just an accident. I don't believe this is an accident. I can't prove it, but nonetheless, it is true. The second idea is that the standard model is somehow incomplete. There's new physics at the electroweak scale, and our model is only good to a TeV or 2 TeV or 5 TeV or something. Beyond that, something different is happening. Idea 3 is there's some cancellation which makes the radiative correction small. And the usual trick is to invoke supersymmetry, which, if unbroken, makes it 0. Because every time I have a fermion contribution, I have a boson contribution with exactly the same amplitude and exactly the opposite sign, so it zeroes it out. Now, we know supersymmetry is broken, if there is supersymmetry. So that says this only works approximately, but maybe that's not so bad. Right? I don't have to solve the entire I don't have to make the Higgs mass 0. I just have to make it 125. Now, supersymmetry, people like it because it has some nice features. It gives you a natural dark matter candidate, for example. The minimum number of Higgs bosons is 5 because you need 2 Higgs doublets, and we've only got the 1. So, is supersymmetry the answer? You can tell I've stolen the slide because I didn't remove the see this person from the talk, but I did update the slides. So, this is what I didn't want to show you. I did not want to go through and say, we look for this signature in this channel and see nothing, and then we look over here and see nothing, and then we look over here and see nothing, and give you a big long number of channels and limits, because you're going to walk out of here knowing absolutely nothing, because this is not a meaningful thing. What's more meaningful is there space in what we see to support SUSY or not? All right, so this is a little bit more useful, where we say, if there's a stop that weighs this, and if the lightest supersymmetric particle weighs that, if you're here, are you excluded? If you're there, are you excluded? If you're there, are you excluded? And so on. That's a little bit more useful, and it tells you that, all right, below about a TeV, there are constraints on the stop Squarks mass. All right, you see that as the lightest supersymmetric particle gets heavier and heavier, the constraints get worse. You can kind of learn qualitatively. Now let me show you how to read a limit plot, and now I'll go over here. Not quite yet. I want to talk about SUSY is a theory that has 10 zillion parameters. People argue about whether it's 60 or 100 or 120. There's a lot. it's helpful to think about three things phenomenologically. These are the guys we're looking for. So the conventional model says there's three degenerate squarks. Why do they make them degenerate? Well, they got to weigh something, and, well, we just made them weigh the same. Heaviest supersymmetric particle that's relevant is the gluino. It decays to a squark, which ultimately decays to this lightest part. Here we have naturalness, the natural SUSY. Only the stop squark is light. Now think about the radiative corrections to the Higgs. They are sensitive to this new scale. So it's sensitive to the top scale. What does the top quark do to it? And that's canceled by its supersymmetric particle, the stop. The other guys can be wherever they want. Only these two guys matter. That's the idea. Some of the alternatives are just ugly, right? It doesn't have to be the stop. It could be some other random scalar that does it. But that just seems, well, kind of needlessly pointless. Then there's what I call the electroweak scale SUSY, where it starts out like the conventional guy, but I make the gluino really, 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 really heavy. If I make it so heavy that we can't produce it, you don't get these cascade decays, and you're producing the squarks, but you're producing them because they have electroweak quantum numbers, not because they have color. So those are the three kind of models that we have. Why did I bring that out? Because if you go in that direction, the cross-sections get bigger and bigger and bigger. It's easier and easier to make them, so the limits become stronger and stronger. And conversely, you go the other direction, right? The cross-sections get smaller and smaller, and the limits get worse and worse. So I showed you a limit plot. Let me try and describe how to read it. So in general, you have one particle's mass over here. You have another particle's mass over there. And the allowed region is outside of this curve. So we're saying if something was living there, we would have seen it. Because we don't, we can set a limit saying it must be past this. Now, out here in the dashed line is the expected limit. That is, if we ran a zillion atlases and a zillion CMSs and there was no new physics, this is the average spot that the limit would line up to. All right? The observed limit is here in the red. So it's inside of the expected limit. So did we do better or worse than the expected limit? 50-50 shot. Should I pull someone at random? Worse. We did worse. So did we see fewer or more events than we thought? No, we saw more. Right? Because we saw more events, our ability to set a limit, a statement that we did not see it, is worsened. Is that clear? All right. Now, of course it's clear to you. You're a famous professor. Is it clear to you? All right. So one of the reasons that we do this, and if you don't like this, I'm partially responsible for making people do this, is I think it matters not just where you set this limit, but for people who are looking at this, kind of understand the basis behind this. Right? We saw too many events. Well, that might mean we're starting to see a signal. That's important. Right? Now, suppose we do better than we thought. All right, fine, that happens, right? Half the time you do worse and half the time you do better. But suppose we did a lot better. So if I said, I think my background is 100 events, and I understand that 100 to maybe 20%. That's a sort of statement that we might say. So if we see 90, say, okay, we got a little bit lucky, and we'll move the limit out a bit. Well, what if we saw 50? What if we saw 20? What if we saw 10? At what point is my statement that I expect 100% start to get a little fishy? So let's just do this with hands. So I say 20, I say you expect 100% and we see 100, or 100 events and we see 100. How many of you are okay with that? Every hand should go up. Every hand is up. Okay, 90, 80, 70, 60, 50. Okay, so you see two things. One is there's a point where you kind of lose faith that we know what we're talking about. And at that point, you start to wonder, maybe the expected limit doesn't mean what we think it does, and maybe I should treat this skeptically. The other thing you should notice is you all took your hands down at roughly different spots. There is no convention in this field to say this is the point where I believe you know what you're talking about, and this is the point where I believe that you're full of crap. Everyone has their own opinion about how far you can go down that path, right? Which is why we want to tell you that, okay, this is what we expect, this is what we expect, this is what we see, and let the reader of the paper determine for themselves, do they believe what we're saying makes any sense or not. Next question. I have two particles here, but of course SUSY has more particles. Every particle in the standard model has a partner and then some. So why is there only two there? And the answer is we don't have enough data or enough computing to slice our data in many different ways. So in general, when you're looking at this, we make some other assumption or set of assumptions and then say, let's relax it for these two particles. Right? That means that there are assumptions built into these plots which are not written on these plots. So I call these the limitations of limit plots. Every particle has model dependence built in. Typically, they assume that the only thing that we see are the particle we are interested in setting a limit on, and it decayed in a particular known way. This almost never happens in real-life models. Almost never. So for example, if you believe that you can have a stop squark decay to a top quark plus a light supersymmetric particle, you also may have the case where it goes to a charged guy and gives you a B on the other end, depending on how the masses work out. Right? So we generally assume that the particle we produced does only one thing when it decays, and as I say, it's the worst possible assumption except in all the others. Because at least here, you know that the number that you have to correct is 100%. Whereas if we had a more complicated thing, it might be very hard to figure out what that correction should be. So that's why we do this. We do not do this because it lets us set better limits than our competition. That's just a fortunate side effect. So, while many particles seem to exclude SUSY below about a TeV, this is not ironclad. There are certain sets of parameters where we would be producing particles and not noticing that we're doing it. So, another way you can look at this data is you take an n-dimensional parameterization. 11 is popular, 19 is popular. And you look at all of the possible measurements that we have. So you look at the LHC, you look at cosmology, you look at G-2, you say, all right, has this been excluded by the data? For example, this would overclose the universe and we wouldn't be around here to build an LHC, so this point gets marked off. All right? It doesn't really matter what numbers here happens to be the mass of one particle and how much it looks like the partner, in this case of the B, the unbroken U1. But you can see a couple of things. First, you see some structure to this. Right? This structure usually occurs because one measurement is constraining it down here, another different measurement constrains it over there, and so on. You are regions where it's purely white. Those are probably really excluded. Not a single point there survived. That tells you something. The fact that things cluster here tells you, I would say, nothing. 10,000 wrong models don't tell you anything about the one right model. Right? The person who made that plot doesn't like me saying these things, but I think that's the right thing to say. The fact that the densities get low here tells you this is allowed, but you're coming up against some other constraint that's not on this plot for those kinds of models. So you can get, this is a different way of looking at things than the limit plots. You can just say, out of all of the possibilities, which ones survive, which ones don't. I like the approach. So, I had to put a quiz in. So this plot, this axis is the content of the lightest partner on the partner of the B. This is the partner of the Higgs. Right? Together, there's something you should notice about these plots. Anything? Anyone? Anything? One is red, one is green. They look like a flip of each other. And the reason they're a flip of each other is ultimately you're constraining to about 100%. So if this particle is 60% one and 40% the other, right, that same point exists in both plots. So all of these plots are very strongly coupled with each other. There's really no way to get around that. That's just how we are. All right, so I would say the SUSY story has come to a middle. The LHC has neither discovered SUSY nor eliminated, but it's constrained it. And the models that are easy to spot have all been excluded. And we can, like I said, we'll be happy to discuss over a beer whether it's likely that nature would arrange things that way and if that question even makes any sense. I think the answer is no and no. There's a typical characteristics of these surviving models, and that is much of the spectrum tends to be heavy and hard to produce at the LHC. All right, that's not crazy, right? We didn't see it, so there must be a reason for that. To stabilize the Higgs mass, you only need the stop quark to be light and the gluino to be moderately light. So it's not crazy to imagine that it's arranged itself this way. And the other thing that tends to happen is the lighter particles tend to be close together in mass. And this is one of the things that Steve Martin at NIU and I worked on. Basically, it makes their decay chains hard to see. So I showed you those jumps. If you've got big, fat jumps, you've got a lot of energy at each step, and it's easy to spot that in your detector. If everything is sitting right up to each other and you've got 2 extra pions, you're never going to spot that. So that's just, these are what the surviving models look like. All right, the last thing I want to talk about is beta mu mu. This is also learned from the LHC. In the standard model, these decays are Jim suppressed and they decay through loops, some of which I've put up there. To give you an idea of how rare these decays are, so the B decays in, let's see, about 150 picoseconds. These are probing partial lifetimes of several seconds. So if the only thing the B mesons would do is decay through this mode, they would live for macroscopic times. But in fact, they decay a billion times faster, several billion times faster. And you've got all these diagrams here. All right. In BSM, like the bottom two, beyond the standard model, those amplitudes can compete with the standard model and can even enhance things. So if I have, typically this goes as tangent beta to the 6th. So if this has an amplitude of 1 and tangent beta of 10, this has an amplitude of like 1,000,000. So this is kind of an interesting thing that you might want to look at. Even if you have other suppression factors, 1,000,000 is hard to get rid of. So here's what the data shows. So the signal is very weak. There's 3 decays per billion. And the first measurement came from, if I made her leave? Wow. It's not your job to make sure that I sometimes use this slide. 3 decays per billion. So the first observation took 2 experiments to put their data together. We tend not to like to do this because now how do you check that one did it right? We like to keep them independent, but if you don't have enough data, you don't have enough data. Now that there's more data, single experiments are starting to show compelling signatures. So we can see the decay, beta mu mu. This is good. Here's the bad news. The production rate is right on the standard model. Right? And that means that any new physics that you have is limited to having an amplitude that's about half of the standard model. Right? This is surprising because, like I said, there are these large enhancement factors in here. Did I say yes? There's an anomaly here that got people excited about, I'd say 10 minutes after this plot came out. So there are actually 2 particles here. This has a B and an S quark in it. This has a B and a D quark in it. And people were saying, the bottom guy is huge. All right, so something is happening here that's new physics. So first, it went away. Now, it wasn't just marginal, but you're guaranteed to have an upward fluctuation. Because if it's right at the threshold of sensitivity, the only way you see it is with an upward fluctuation. If you have a downward fluctuation, you miss it entirely. So the way we do science conspires in such a way that we spot upward fluctuations. Every time a new particle is discovered, the production rate is high. Every time the last limit on that is produced, that last limit is too good. And the reason is, if you have a downward fluctuation, you write a limit paper, and if you have an upward fluctuation, you write a discovery paper. So you've got these fluctuations built in because it determines the title of the paper that you write. So it's worth being aware of that. All right, flavor conclusions. This is just a taste of flavor physics, pun intended. It wasn't even that funny. So, what do we know? There are other B decays. These are exploded at the LHC and the B factories. There are rare decays outside of the LHC, kaons and Ds. There's really some remarkable things going on in K decays, looking for the decay pi 0 nu nu. Nothing is in your detector. This is big. There are searches for rare muon decays. Nobody's ever seen them. And there are precision measurements like G-2 of not just the muon, but also the electron puts strong constraints on this. The picture that's coming out of flavor is that the expectations match the standard model to a very high degree of accuracy. And if you want to put it under a scale of new physics like I did with the lambdas, you get some number like 10, 20, 30 TeV. Right. Now, the Higgs mass, to make sense, there needs to be some new physics around a TeV to constrain it. But flavor is telling us that nothing odd is going on until a scale of 10 or 20 or 30 times more than that. So there are ideas for why this might be, but for whatever reason, the new physics that we think has to be there in the Higgs sector is leaving its fingerprints off the flavor sector. So that gets me back to my third slide. So the conclusions are there are exactly three generations, that nature's given us a fundamental scalar, and as far as we can tell, it looks like the standard model Higgs, and there is absolutely nothing about its mass that makes sense. And finally, that mass suggests that there's new physics at the TeV scale to fix that, but flavor is telling us that that scale is more like 10 or 20 or 30 TeV. And I believe that's it. So thank you very much. You better ask questions, otherwise I'm going to just grill you. Yes?
So you emphasized how little sense the Higgs mass makes, but I thought that there was also essentially an upper bound of about on the Higgs mass for the electroweak theory if it's recovered.
Right. So there is the Higgs has to weigh somewhere less than a TeV for it to do its job. Nevertheless, once you have a fundamental scalar and say, okay, this is what it's doing, you have to ask the question, why are the radiative corrections not driving it up? I mean, in the world that we're postulating here is that nature gives us a Higgs. New physics at the Planck scale drives its mass up to something that's bananas. It no longer breaks electroweak symmetry. And now we live in a world that doesn't look anything like ours. So in some sense, we knew that there was a problem long before we discovered the number was 125. The fact that the number is finite to first order is already a deep problem with the theory. Because once you give a particle the quantum numbers of the vacuum, it can touch everything. So there needs to be something like SUSY which throttles this down. Right. The other thing that I probably should have said better than I did, since we're talking about radiative corrections, this is an opportunity for me to correct a mistake. The fact that the Higgs mass is above the Z mass tells you that radiative corrections are large. Because that was a tree level statement, and when you apply radiative corrections, it goes away. Well, that's all well and good, but now that we've decided that the radiative corrections are large, what stops them from being even larger? So that's why I say it's too light to be heavy, because it's not sitting at the Planck mass or the gut mass or something. But it's also too heavy to be light, because you would really like it to be sitting underneath the Z mass where the tree level calculations tell it to be. And radiative corrections drive you out of both of those spots that make sense into where we are now. Yes? So this goes as roughly the square root of the data that you correct, because you're doing counting experiments and you're comparing two channels where you see it. So by the end of the LHC, when I will be dead, or wishing that I were, that by that point we will collect roughly 100 times as much data as we've got. You take the square root of that, and that's some number like 10. Now, what ends up there are two competing factors. One is there are sometimes systematic effects which keep you from doing better, but you also have smart grad students who need to get their next job, and they work very hard on beating these things down. So it's, 10 might be 8 and it might be 12, but that's the sort of number. So we would expect by the time we're done, I would say at the 5-ish% level, to say that this is what we see. And 5%, there's a lot of numbers that could be near 1 that end up being 5%. Yes. Yes. So that 100 is assuming it's the full high luminosity LHC of 4 attobarns. And I didn't even know what an attobarn was when I started this. It's a truly shocking amount of luminosity. When you see how the experiments have to survive that much damage to their detectors, it's really remarkable. And I'm saying that as if it's already done, and it hasn't. It's much easier to talk about the great things that you're going to do than what you've actually done. More questions? I see people kind of doing this. It's okay. I mean, we can turn the recording off. It's not like you're a famous dean or department chair somewhere. We're going to get this out and say, hey, yes, that. I mean, yes. What are the no? All right. So let me just a couple of things. First is this is not the job that I thought I was going to be getting into. I think first of all it's important to realize that. So let's start with some facts. So anyone remember Schoolhouse Rock? I'm just a bill. Okay. And the Saturday Night Live parody. I'm just an executive order, and I pretty much just happen. Right. So let's talk about what happens. So the president submits a budget. Congress then takes a look at that budget and says, this part we like, this part we don't. The House passes a bill that says this is what the budget is. They hold the power of the purse. The Senate passes a bill that agrees with that, and if not, they go back and loop until they do, and then we go on. So the current budget for HEP from the Department of Energy is something over $800 million a year. So we get almost $1 billion to do science. The president's budget is $672. So there's about a 15% cut. So what can I say about this cut? First, if 672 is enacted, I am still deeply grateful to the taxpayers of the United States of America to give us $672 million to do science. And we are going to do the best science we possibly can given those constraints. That said, the amount of science you can do for 672 is not the science that you can do for 868, for example. So there will be deep and painful cuts. And part of my job in the agency is to do the best I can to ensure that these cuts are temporary. Because what we don't want to do is go down a path where we have to fire a bunch of people that have critical knowledge to bring our program forward, and then a month later try and hire them back. Right? The technical term for this is stupid. Right? We should not do stupid things. So we're working as hard as we can to try and mitigate what's going on as we go from various steps of the budget, and we expect that things will, in some cases, go up, and other places they'll go down, and we're going to have to kind of navigate this road until we get an actual budget, which, as you know in Schoolhouse Rock, happens when the president signs the bill, right, which will, if it happens before September 30th, this is good. Otherwise, we go into something called a continuing resolution, where we wait until Congress manages to come up with this level of agreement, and there are different rules for all of these things. I highly recommend Schoolhouse Rock. The guy who did that, Bob Dorough, is 93 years old, and he's still performing. So, does that answer your question as best as I can? I like to think of myself as a young person. It is not true, but I like to think of myself as a young person. So one thing that people should be made aware of, and it's not really in the culture, is that 90% of the people who get degrees in particle physics end up with a career that's not in particle physics. All right? This comes about because a professor has 10 graduate students over the course of his career, only one of which is needed to replace him. And in good times, that one might become 1.5. In bad times, it might become 0.6. But this is the general thing. This is the same. Anyone believe in vampires? Right. This is the same problem. if there were vampires and you're bitten by a vampire and you turn into a vampire, pretty soon the entire planet would be hip deep in vampires. So we know there aren't vampires because that's not what happens. The world is not hip deep in professors. Right? So you don't have this level of exponential growth. One of the reasons Congress likes, it actually does connect back. One of the reasons Congress likes to fund particle physicists is when we leave doing particle physics and do other things, the country gets great benefits from that. Right? So I have had a former student of mine teaches high school. I've got another former student who works for Boeing to make sure that the Dreamliner doesn't explode when it's hit by lightning. This is a big, complicated project. A student I worked with works for Motorola making cell phone antennas slightly more efficient. Verizon spends $2 billion a year putting cell phone towers up. If you could increase the efficiency of antennas so that they could cut that by 5%, this is serious money. So the reason Congress thinks this is a good thing to fund is not because they have a deep interest in electroweak symmetry breaking. As much as I would like that to be true, it's because people come here and the normal career path is not to be a professor. The normal career path is you come in, you study something and write your dissertation on it, and then you go off and do something else. And it's that something else that they like. That's just where we are. And it's, we might prefer a world that's different. I had a friend who said, I see where you're coming from, but I think what we should really do is once I get a faculty job, that's when we have to start turning the knobs back on down. And the problem with that argument is it's self-similar throughout time. So it's important to realize, that we are, part of the things that we do really do provide value to the country as a whole, and that this is seen by Congress as a good thing, even though it might not seem like a good thing to us. Yes?
A follow-up question. So
You didn't beat me enough up with that one? No, that was the one. I mean, I'm coming here all bloody after that.
Well, my naive understanding was that in the 2017 budget, science didn't receive the kind of, like when Congress actually had their way with the 2017 budget, they kind of saved science. Is there a reason for us to believe that that will or won't happen the same way in the 2018?
So, a couple of things. First, there's something called the Hatch Act. That means that while I work for the federal government, I cannot encourage you to contact your congressman or lobby in any way. So I want you to understand that I'm not allowed to do that. That said, I can't, for the same argument, I can't encourage you to do this, I can't prevent you either. Right? It's important to understand Congress's role in this. In 2017, one of the 6 science offices in Office of Science and DOE did better. All the other ones got cuts. The one that did better was HEP. And part of the reason is Congress knows that we have gone through a painful exercise in P5 and saying these are our priorities. These are the things that we absolutely have to do. These are the things that we would really like to do. And these are things that, yes, if we're walking down the street and a drug smuggler's plane drops $1 billion on our feet, then we would do that. Maybe. But having gone through that exercise, they're very appreciative of this because now they're getting advice from the community of what they should, what we think is important, why we think it's important. And that was very, very successful. So one of the reasons I believe, and this is just my opinion, that high energy did well with respect to the other science offices is we made a better science case. And I think if you think about this as ultimately the resources to do our science is coming from the American people, we have to make our case to them and explain that, yes, it is better to give us X dollars to do this than to get that extra latte from Starbucks or whatever. Because it really is, we are asking them to make a sacrifice to help us. And we need to be responsible if we're going to do that. Schoolhouse Rock. Any other questions? We're all out of electrons for the recording of this, right? If I'm carted off to prison. I could. But unfortunately, I cannot turn my mic off 10 minutes ago. Is anyone an expert in closed time-like curves in this room? At least I'm in the best spot to ask that question. More questions. This may be the last time you ever see an experimenter up in front of you. We don't, well, we're not as bad as you've heard.
Would directly detecting supersymmetry help a lot? I mean, funding and stuff?
The Higgs didn't really. So first of all, the idea, it's not like we're going to say, if we could just inject a few events over here, then our financials will be fine. All right, so let's not talk about that. I think if nature turns out to be supersymmetric, I think that would generate a great deal of interest in our field. But as I just said, that doesn't translate into growing the professorhood. All right, so I think this would have some positive impacts on how this is perceived among the funding agencies. I think it will have positive benefits to the people who are doing this work, but they may not see it that way. Because for most of us, this is not a lifetime job. Even me. I've had a very successful career, but what do I do now? I do budgets and schedules to make sure that other people can do science now. Right? I expected that I'd still be running n-tuple analysis into my 50s and 60s and die the world's oldest and happiest postdoc. But in fact, what we all have to say, okay, our careers are going to take little zigs and zags to get, to make sure that what happens, what needs to happen happens. So that's why I'm spending 2 years in Washington, for example, where I should have been spending, in some sense, I should have been spending that time doing research, but I'm doing the best I can to make sure that in these budget situations that we're left with a field as a whole doing that. And other people have gone off. One of my grad school buddies works now at JPL, but he's an expert in adaptive optics. Nothing to do with high energy physics at all. But if you can solve the sorts of problems that high energy physics presents to you, you can solve a large set of problems that people are actually willing to pay real live money for. That probably didn't answer your question, but at this point, all I really have to do is run down the clock. Yes. I'm sorry. Yes.
So I was just curious about the Great Collider project in Canada and whether or not this kind of physics in the U.S. will remain competitive.
So I think the reason that China is interested in building this collider is not because the Chinese have a deeper interest in electroweak symmetry breaking than the Americans. I think if you take a look at this room, you will see a lot of Chinese faces. People come from China, come here, learn something. They send their best and brightest here. They learn something, and they stay in America. Not all the time, but a large fraction of the time they do. If I were in the Chinese government, this would really cheese me off. Right? So I can see them wanting to build a large scientific project in China that does the reverse, brings people from all over the world who then sit and say, hey, I like it in China, I'm going to stay in China. Whether this will be that project, I am much less sure of. Right? A lot of things could fit into this space, and a giant collider is one of them. I think what the LHC tells us a lot about whether a large circular machine, a large circular proton machine, makes scientific sense or not. Right? Suppose the LHC was a complete desert. Right? The Higgs was the last thing we found. We run till 2036. How many of you would then say, clearly we just need to push a little bit farther along the same front? Hands. What the heck, hands? Okay, so a few people think that, but the majority doesn't. And I think that many people would be saying, maybe we should be thinking about dark matter, precision measurements, this, that, or the other thing, if that's the world and not a giant PP collider. Yes?
Do you think there is, suppose nothing comes up at LHC year after year, isn't there still a strong case for some kind of Higgs factory which will do more precision physics, or you think it's not?
So if nothing comes up, I would be thinking about things like a Higgs factory. I'd be thinking about also even old ideas like a GigaZ, a machine that makes a lot of Z's. I would be thinking, all right, it's probably not right to push on the energy front until we take another look at precision. I would be thinking about doing a lot more precision flavor because, as you heard, my opinion is that the challenge of this you guys, is to sort out the issue of why there's this disparity in scales between what the Higgs seems to be telling us and what flavor seems to be telling us. And I think the case to be doing a lot more precision flavor can be made if you think that would help answer this tension.
It's also partly already at the super bell.
So Bell 2 is trying to increase this, but the problem with precision measurements is how precise is precise. How you need to measure something that you know is right, and there's a lot of measurements out there. I can go on all night. Don't worry about this. Like take DAMA. DAMA has a 9 sigma significant measurement. There is nobody outside the DAMA collaboration that believes they've discovered dark matter. Right. So precision by itself isn't enough. You need to be able to tell a convincing story, right? And if they were to launch an experiment on the southern hemisphere that showed a 3 sigma signal, all of a sudden people would be much more willing to believe their 9 sigma signal. So it's not necessarily even a single measurement. The ensemble of measurements is important, and boy, I really hope it's off now. The credibility of the people who are telling you they've made this measurement is important.
What do you think is the plausible time scale for this decision? What's the next? Is it like 2 years, 5 years?
I don't have a good
The whole worldwide high energy community has to decide.
I think that the measurements that we're making now are going to tell us that. If, for example, G-2 reproduces the Brookhaven measurement with a smaller error bar, people are going to start not just saying, oh, maybe there's some hint of new physics, but are going to start asking more useful questions like, dear LHC, you're not looking for this right this second, but you should, because if this model is right, you'll see this, that, and the other thing as well. So, there's a lot of these 2 sigma anomalies out there, most of which I don't believe, but one of them eventually is going to be right. One of the things I said to the phenomenologists is most 1 and 2 sigma signals never grow up to be 5 sigma signals. But every 5 sigma signal began life as a 1 or a 2 sigma signal. So it's entirely possible that there's some anomaly in the data that we might not even recognize now that's the key to understanding how this all goes together.